So in this problem we have a bucket that is suspended over a well by a winch and rope. The winch consists of a solid cylinder with a mass M and radius R, about which the rope is wrapped. Then it says that a handle is attached to one end in order to rotate the cylinder. For the purposes of this example, we are going to ignore any frictional forces in the winch. Now it says that suppose that the winch handle breaks off, allowing the bucket to fall to the water as the rope unwinds from the cylinder. They're asking us to find the speed of the bucket and the angular velocity of the cylinder just before the bucket hits the water. Now, assuming that the water level is at depth h below the bucket. Now, before the bucket draws, we have two things. We have the potential energy, the initial potential energy equals mgh. And the kinetic energy, the initial kinetic energy is going to be equal to 0 because it's at rest. After the collision though, when the bucket hits the water, we have the winch that is going to rotate. We have a final kinetic energy being equal to 1/2 times the moment of inertia times the angular velocity squared. In respect with the bucket, the final velocity, the final kinetic energy is going to be equal to 1/2 times the mass times the velocity squared. In addition, we have the final potential energy is going to be equal to 0. So to find the total kinetic energy, the total final kinetic energy, we will have to do the sum of both kinetic energies from the winch and the bucket. So we have 1/2 mass times velocity squared plus 1/2 moment of inertia times its angular velocity. The good thing is that we can rewrite the momentum of inertia to 1/2 times the mass times the radius. Although the problem to find the final kinetic energy is that we have two unknowns. We have one unknown for the velocity and then one unknown for the angular velocity. Fortunately, we know that the velocity is going to be the same as the radius times omega, but we can rewrite omega as a velocity over r. So as we continue solving for the total kinetic energy, we have on the left side we have the initial kinetic energy plus the initial potential energy being equal to the final kinetic energy plus the final potential energy. As we said first, the initial potential energy is going to be mgh and the initial kinetic energy is going to be 0. Then the final kinetic energy is going to be 1/2 mv squared, and the final potential energy is going to be this whole thing written right here. This part represents the I, the moment of inertia, and this is what we just did up here. The v over r squared representing the omega squared. Then as we continue solving for the problem, we get rid of the r squared on the right side, and then we can continue by factoring out the 1/2 v squared. So as we continue to find the velocity, we end up with the square root of 2 mgh divided by m plus 1/2 of m. However, if we can simplify a little bit more, we can just do a little bit more of algebra, so we can cancel the m on top, and we end up with the answer of square root of 2gh divided by 1 plus big M over 2 little m. So that was one thing, that was the velocity, but now the angular velocity is going to be equal to the following thing that's written right here. This whole thing.